All right, so we have 4 classes left and then a final exam. So we're kind of getting to the final stretch here. Just as a reminder, our exam is on that Monday. All right, so you don't really get a long period of time. Our last lecture is on December 6th, and your final's on the 11th, so not a lot of time there. I do think we're going to finish the book. I don't see us having any issues getting through all the sections. As long as we can keep pace. I think today we'll finish up 13.6, and then we'll start 13.7 on Wednesday. 13.7 and 13.8 will take us 2 days, and 13.9 will be 1 day. So I think we're good. Last class, we were trying to come up with parametric equations for drawing surfaces. And I had a handout, right? You'll have that? And I want to continue what we were doing. So we have a cylinder here. Now, it's hard to see this on your page. Oh, I had a little relapse. I started to get better, and then last night I started to feel bad again. So I don't know what's going on here. I was good all the holiday, and then last night, that's weird. So I feel fine. It's just that sound terrible. So, all right. So we have this cylinder. It's hard to tell on your piece of paper where this thing is. So let me clarify. This is a cylinder. It has a radius of 1. And also, if I turn this to the side, notice that it does not actually touch the XZ plane. It is at 1. At what equals 1? Can you all tell there? Where does it look like it goes from? From like 1 to what? It is 1 to 4. It's hard to see it, but it is 1 to 4. All right? I just want you to be clear on the fact that that doesn't go all the way back to the XZ plane. So if we're trying to come up with a vector function that will draw this, is there anything that you can tell me? Well, I don't know. What can you tell me? I can tell you what it is, but let's think through this. Anything about these component functions? Remember, you have control of u and v, right? Those are the 2 variables you can control. So, any ideas? So if you're looking at it straight down the y-axis, right? That's what you're saying here? That really that cylinder is just a circle, a unit circle, right? So you need to be able to draw a unit circle, which would just be cosine u, sine u. Now, which variables would which component functions would need to draw the circle? X and z. So how about we just do cosine u here and sine u here, and then we restrict our u between 0 and 2 pi, and that should draw me circles, right? Yeah? But what about the y component? What do we want the y component to do? So we move, right? We want it to be able to move. So we want to be able to draw, like, how would you draw this outer edge, this outer ring right here? What would your y value need to be there? 4, right? And then what would the y value need to be if you want to draw this one back here? 1. And then if you wanted to draw all the circles in here, right? Then you just basically need to move that y coordinate back and forth between 1 and 4, right? So our y component function should just be v, and then let v go between 1 and 4. And a way that you can, again, check this is to just like fix a v. If you let v be 1, then let u go from 0 to 2 pi, you draw that first circle. And then just start to vary v, and you can see it kind of draw all those rings together. Okay? We good? All right, let's move on. This one right here. This is the exact same picture, but I just want to know the vector function that would draw the n cap, which is that part in red. So if I flip this around, it's hollow, okay? I just want to be able to draw this red end cap here, which is different than drawing the cylinder, isn't it?
Yes.
But that is the same cylinder from the previous example. So this time, the difference, what's the main difference in this one compared to the other ones? The y is what? It's fixed, right? The y is fixed. It's always 4. So I know that right away. I can fix this at 4. It's never going to change. Right? Now, when I draw this cap, everyone agree I need to draw the unit circle? Yes. But I also need to draw every other circle all the way down. I missed completely, but it's okay. Right? I'm supposed to draw all those circles together. So there I have a varying radius, right? And the radius is what appears in front of the cosine and the sine. But again, I have 2 variables to play with. So let me go u and v here. What do you want? V cosine u. And then here, v sine u. U would go between 0 and 2 pi. And v would go between 0 and 1. V is the radius of the circle, right? And I want that to go between 0 and 1. Yes?
Yes.
Now, just so we're all clear, could you have done this? U cosine v for u sine v, and would that be the same thing? As long as you switch these around, make this one your v and this one your u, then it's okay. So you have the freedom to control those variables. There's nothing that says u has to be the angle and v has to be the radius. Two variables, you get to do what you want with them. All right, let's move on. Okay, for this one, I need to give you some additional information before we can do the problem. So let me erase this. Okay. All right, so let's look at it first. It says, find the vector functions, plural, which yield the 3 surfaces shown here. So let me just kind of spin this around for you. Look at it from the side a little bit like this. Oh, maybe. Come on. Boy, it's acting really funny. All right, I'm never going to be able to get it back. Jeez. Oh, man. Okay, red, positive. There it is. Okay. Got it, finally. All right, you got it? Now, I need to give you some information about this before we can actually do the problem. Again, this will be a radius of 1. And then you see this, looks like someone came and sliced through the cylinder with a plane, right? A plane. And that actually has an equation. The equation of that plane is x plus y minus z equals 2. That is the equation of a plane, isn't it?
Yes.
Okay. And then the back side here was a plane also. That back side, it's the xz plane, which is y is 0, isn't it? Those are your 3 surfaces. The back cap, this front kind of slanted cap, and then the cylinder itself, right? That's been cut. All right, so let's start with the easiest surface. What do you think is the easiest surface there? The y equals 0. Let's call that one S1, surface 1. Let's call this one over here surface 2, and the actual cylinder surface 3. So we have to come up with 3 separate vector functions. So for S1, I'm gonna come up with my vector function. I'm gonna call R sub 1 UV. So R sub 1 is just so it corresponds with surface 1. We need our 3 components. So which component there is easy? The y, right? It's 0, right? Because it's sitting on the xz plane. And then the back side of that is a disk, right? A disk, which we just did in the previous example, didn't we? It has a variable radius and a fixed y coordinate. So, what is it? I didn't hear. V cosine u, v sine u. Wouldn't that work? So long as we restrict these properly. So what are my restrictions? U is going to be 0 to 2 pi, and then v will be between 0 and 1. Okay, that will take care of surface 1. What about surface 2? Surface 2 is a little different, isn't it? Because it kind of looks like surface 1, doesn't it? So when you draw surface 1, if I turn this and I look at it straight from this side, don't surface 1 and surface 2 look identical if you look straight down the y-axis? You wouldn't be able to distinguish the two, would you? If you look just straight down. But there is a difference. Surface 1 in the back, the y-coordinate is stuck at 0, right? Yes? But on surface 2, the y-coordinate is actually varying, right? It's changing. And so this y that used to be 0 now needs to be something different. But in terms of the x and z, we still need to draw circles. Okay, so it's kind of like, I need to draw a circle. I'm trying to do S2. I'm going to try and draw a circle right here. That's the outer edge of S2. But as I'm doing it, I'm actually changing my in and out, right? From the y-coordinate, I'm changing that, but I'm still drawing the circle. So how is that y-coordinate changing? Well, it has to live on the plane, doesn't it? And the plane has an equation. So what are we interested in? What part of it are we interested in? The y, right? We want to know what the y is because the y it used to be 0, but now it's going to be something else, right? And if I solve that equation for y, I would get y is equal to 2 minus x plus z. Agreed? Okay, so let's go back down here. Let's draw the circle first that has a varying radius in the xz plane, which would still be our v cosine u and our v sine u. Right? That's still drawing that circle with a varying radius. But the y-coordinate needs to move, and that will be a function of both x and z, won't it? Depending on what my x position is and my z position, that determines my y position. So this y component should be what? 2 minus x, but what's x? V cosine u plus z, which is v sine u. Sorry, I ran out of room there. Does that make sense? 2 minus x plus z. That's a v right there. What about my restrictions? Same thing. Does that make sense? Okay. Will I be able to get this back? I'm all jacked up again. Come on. I need to redo these, this code up here because there's a way you can change your viewpoint. Well, I have it in here though. I don't know why it's not going back to the default viewpoint every time I rerun the code. Oh well. Okay. Good? S3. All right. S3 I say for the end because S3 I guess is the most complicated one. The big difference between S1, S2, and S3 is that with S1 and S2, you're really drawing these disks, right? With a varying radius. And that eats up both your variables, U and V, to do that, right? But with S3, you don't have a varying radius. It's just the outer shell of the cylinder. Understand? So we only need one variable to draw the outer ring, because the outer ring of this thing, right, is a circle with radius 1, which I can draw with relative ease. Yeah? Because I don't have to make it go in and out, yes? Okay, so what can I say about S3? S3, I'm drawing circles. Man, that marker just keeps on making its way back here. I'm drawing circles in the XZ plane, right? That would be, I guess, parallel to the XZ plane. So how could you do that? Cosine U, and then sine U. Everyone agrees that's just going to draw me circles radius 1. Now the question is, what happens to the y coordinate? It's between where? Okay, so let's imagine this. Right now, U is going to be between 0 and 2 pi, right? We know that because that's going to draw the circle. So let's fix a U, okay? Let's fix a U real quick. Let's fix a U. So give me a U. Pi? Okay, so if U is pi, where are we? Cosine pi, sine pi. Where are we at? We're at -1 for x. And where are we for 0? So that would be like back there, right? That's where we would be? But what about the y coordinate? We're at 0 there, but like this doesn't tell me that, right? What do I actually want my y coordinate to be? Yes, but visually. A line, how? Explain. You want that line to go where, though? From the back of this all the way out to, boom, that front edge, right? Somewhere in there? Yes? So that y coordinate needs to be between 0 and that plane, or both planes, right? Let's pick another value. Let's go with 0. Cosine of 0, 1. Sine of 0 is 0. So that would put me at this point over here, right? And now I want my y value to go between 0 and, again, stop somewhere on that plane. You see that? Yes? Every value between those two. So what am I going to put here? Just v. Just v. And then what's v have to be between? 0 and the plane, that other plane, which is 2 minus cosine u plus sine v. Sine u, sorry. So if I fix a u, then my v is allowed to float between 0 and whatever I get when I plug u into the x and z components and get that plane, right? So I've used up all the variables. I've put the appropriate controls. We're in business. Any questions? All right. Let's move on. All right, I need to give you some information for this one. This is x squared plus y squared plus z equals 1. And then the bottom of that is closed off, okay? So we do have a little surface on the bottom. I'm afraid to move it, but there it is on the bottom. Okay? So we want to find the parametric equations or the vector functions that will draw this surface on the bottom. I'll call that S1, and then this one, let's call this S2. So why don't you try and do S1 and S2 on your own, and I'll give you a minute. See if you can come up with it, and then I'll put the answers up here. And we are recording, yes.
So that thing's hollow?
Yes, it's the surface only. We want the outside surface. Yep. I'll give you just a second. I'm just going to get some water. These should look very similar, right? Did y'all get that for S1? Okay, what's the difference between S1 and S2? There's only one difference. The Z component is a different function, right? The X and Y components are exactly the same. So V cosine U, V sine U. And then how do you determine the Z component?
You solve for Z.
solve for z on the surface up there, right? That top surface, S2. So we get 1 minus x squared, right? Which would be v squared cosine squared u minus v squared sine squared u. And then you could use some Pythagorean on that, couldn't you? You could factor out a negative v squared out of these two, and then use a Pythagorean identity. So this is really just what? 1 minus v squared. What about the restrictions on u and v? Same thing, right? Same restrictions. Okay, so same restrictions here. Do you all understand how S1 you're just drawing this little disk, right? And S2 you're drawing the disk, but as you draw it, you're pulling the z component up. Yeah? Okay. All right. We have another one. Last one. Well, there's nothing to do. This is what we're doing. We're practicing coming up with these functions because we need to be able to do that. And that's what I said last class. The book just says, hey, you can draw a surface using these vector functions. And then they throw you right into it. And they just expect that you would just get that and just know how to come up with all the surface functions. I like to take a little bit of time on this because 13.7 and 13.8 is very difficult, especially 13.8 is very difficult if you can't come up with these. So if you understand, great, okay? But if not, then hopefully this is helping. All right, let me give you some information on this one. Let's look at it. So the backside looks like it's flat, right, in the xz plane. But then you've got this other plane cutting through here. And then you've got the bottom, which is flat. And then you've got this curvy top, right? So 4 surfaces. And I'm only going to give information on 2 of them. This one right here is the equation x squared plus z equals 1. And this one right here has the equation y plus z equals 2. Everything else you should be able to get just by looking at it. So let's name the surfaces. We have 4, right? Or, yeah, 4, don't we? Yes. We have the backside, S1. The bottom, S2. Let's make this one S3. And let's make this one S4. So tell me about S1. Anything you know for sure on S1? Something is 0. What's 0?
Y.
Because I want to know.
No Y.
Oh, yes. I know. The y is 0, right? Okay, that's for sure. What about the x component and the z component, though? So why don't I imagine that you were able to walk over here and then go around and turn and look at that, okay? If I were to do that from the other side, I would have x is positive would be to my right? So I'm actually standing over here viewing it from this angle, right? I would have x positive is this way, z positive is this way, and then it would look like this, right? And it's a parabola, right? And it's coming from this equation right here, isn't it? And I can tell where it hits the x-axis. It hits at -1 and 1, right? So this is 1 and this is -1. And then this is following the equation z equals 1 minus x squared. If I solve it for z, that's the parabola, isn't it?
So you would have to solve for x on the equation?
Pardon?
You would have to solve for the x for the equation. So
I'm not solving for x. Why would I solve for x?
to find your x value.
My x, so look, I'm going to try and draw this entire surface, everything inside of it, not just the parabola, right? So think of it this way. If I were to pick an x value right now, like let's say I picked 1/2 for x. I don't want to draw just that point up there. I want to draw every point between there, don't I? All the points between here and here. So how can I make that happen? Well, I first pick my x-coordinate, right? So my x-coordinate can be anything I want it to be. So why don't we call it u, all right? And that u will go between where and where? -1 and 1. And then what about my z coordinate of the point? It's got to be between those two, right? It's got to be between, what? 0 and that. So what? V. And then v, I let v be controlled by u. It's going to be what? 0 to 1 minus x squared, but what's x for us? U, so u squared. That draws S1. Get it? Okay. Let's go with S2. Now S2, this bottom piece right here, is that just a rectangle? What's always the same on that? Like what's the easy component function for that one? Z, right? Z is, what's Z? Z is always going to be 0, isn't it? If you're on that little flat sheet surface 2, your Z is always 0. All right, and then what about the X? The X, you're between, you can make that -1 and 1, and then what about your Y? 0 to 2. It's a rectangle. This is like the most basic type of region we can get. So why don't we just call the X component U, the Y component V, let U go between -1 and 1, and let V go between 0 and 2. That'll draw us a little rectangle. While we're here looking at this, I would like for you to think about something. And again, this is for later. If I were to ask you on this back surface S1 what a normal vector would look like. Normal vectors, remember planes, what a normal vector is? Okay? If you're on S1, a normal vector would either point away or in, but it would be orthogonal to this little surface, wouldn't it? Understand? So what would it look like in terms of ijk? It would only have j going, right? It'd be 0 in the I and 0 in the k. Agreed? So it'd be some multiple of j hat. Understand? These vectors would be some multiple of j hat. What about S2? What can you tell me about a normal vector on that surface? It would only have a k component, right? Right? K hat, that's it. It would either be straight up or straight down. Yes? What about S3? Can you imagine what the normal vector of this surface would be? Well, it would change, wouldn't it, depending on where you were on the surface. But what could you tell me? It would be up and then, like, is there any component you could tell me about at all on those? If you imagine going around with a normal vector on anywhere on that S3? Would the I component change? The I component's in the x direction, right? So would I be changing my I component? Yes. Would I be changing the k component, which is up and down? Yes. What about j? No. It wouldn't, would it? It's kind of like, here, I'll use this. This is kind of like the surface, a little bit like this. If I take a normal vector, it's leaking. Then, if I do that vector along like this, right? Because this is flat like this, I'm never going to be tilted. My normal will never tilt like this, right? It's always going to be like this. Now, it's going to change in the I and K component-wise, but there will never be a change in the J. So the J component will be 0. This is important later, all right? Just pointing it out while we've got this nice picture up here. All right, let's talk about S3. S3. Okay, so S3, what? Let's look at S3. Let's walk down here again. Let's walk over here and look at S3. S3 is this picture, right? Without the inside. This time I don't need to shade the inside. What I need to do is go and have some depth to it, right? I need to actually be able to come out and draw these lines that radiate out from that parabola in the y direction, yes? And that means that my y value has to go between this plane, which is y equals 0, right? All the way to what? This plane, which is governed by this, isn't it? Yes? Okay, so let's see if we can't get this. Try and draw me this point that comes up here and goes across like this. So first, I've got to pick my x, right? My left and right over there. So let's call that u. Right? And then get me up to the top of the parabola. How do you get me up to the top of the parabola? So I've picked my u is going to be x. Now get me up to this point right here. So that's the z? What is that z? 1 minus x squared. Exactly 1 minus x squared, because I have to get up on top of the parabola. I need to be there, not everything in between. So that means my z component needs to be 1 minus u squared. Understand? Now, it's my y value that I now need to let float back and forth between two things. And that y value is going to, what are we going to call it? Why don't we call it v? Okay, what's my u stuck between? -1 and 1. Now what's my v stuck between? 0 is, the y value is 0, so 0, and you say all the way out to where? This right here, solved for what variable? What are we trying to control? What component are we trying to control? The y component, right? So we need to solve this equation for y, which would be 2 minus z, right? So I want this to stop at 2 minus z. But what is z? This. 1 minus u squared. I know that that's tricky, but that's the way it is. 2 minus z. That's what that is. That is this thing solved for y. That makes sense? So let's check it. I want to pick a value. Let's pick a value. Let's let u be 1/2. If u is 1/2, then what am I going to do? I'm going to go out 1/2, which will take me to here. Let's do it on this one. I go out 1/2, right, like this. And then what's my z? My z is 1 minus 1/2 squared is 1/4, so 3/4. So now I go up to 3/4, right? So I'm at 1/2, I go up 3/4. And now it's a matter of, remember, y is coming out. Actually, positive y is that way, negative y is towards us, right? Remember where that guy's standing at the end over there. So what is my y value going to be? Everything between 0 and 2 minus 3/4. 2 minus 3/4? 1 1/4 or 1.25? So that means that I'm going to go, x was a half, I went up 3/4, and now I'm going to go between 0 and not all the way to 2, right? 2 would take me out all the way to here. I'm going to stop short. I'm going to go only to 1 1/4. Understand that? How about this? Let's just check that we could draw this right here. What would my u be for this? 1. So if u is 1, what's this? 0. And then now my v is going to go between 0 and 2. So that means I go out 1, I don't go up and down, and then now it's everything between 0 and 2. All right, that's S3. S4 now? S4 should look a lot like what? S1. They're almost the same, except for that y value is fluctuating. So S1, or S4, sorry, should look like S1. We have, I forgot what S1 was. It was U here, right? And Z was V, or Z was V. And U went between -1 and 1, and V was between what?
0 and 1 minus u squared.
0 and 1 minus u squared. So this would still draw me S1 if I fix this to be 0, right?
Yes.
But do I want to fix this to be 0?
No.
What do I want to do?
You want it to be 1. So,
Yeah, so look, this u and v, the way it's defined here and the way we have the restrictions, is going to want to try and draw this flat surface, right? But I need to take every point. Let me erase some of this crap up here. It's getting a little cluttered. Let's get rid of that right there. Okay, so this is going to want to draw this thing shaded in, right? If this was 0. So it's like I pick an x value, and then I'm going to draw a line that goes up, and it's going to shade that line in. Then I pick another x value or u value. It's going to shade everything and then shade, right? But as I'm shading, I actually need my y value to be out here, right? So it's like I pick my u and then come out to here, right? And then shade like this so that y value fluctuates. Now, how is that y value going to fluctuate? It's going to have to follow this equation, right? Solved for what? Y. So 2 minus z. So what's 2 minus z? 2 minus v.
Wait, is that a negative in front of the line?
Pardon me?
Is that a negative?
no, he had an
No, I erased the arrow that was going that way. Okay, this all right? All right, so that gives you a good kind of mixture of the types of surfaces that we could see and how they differ, how you draw them. And now we're ready to move on and continue in 3.6. So we've seen that we can define vector functions in three-dimensional space, and it will draw surfaces, right? And now we feel good about drawing surfaces? Now, if we were to hold one of the variables constant and let the other one change, then we draw what are called space curves, or grid curves. Right? So that's what we were just doing a second ago. I was moving us out somewhere, and then I said, oh, let the other one vary, and it would draw us a certain part of our surface. Those are called grid curves. So here's an example. Here's the first example that you're given in this section. Imagine if we hadn't talked about anything yet about space curve, about surfaces and parametrics, drawing them parametrically. and then I throw this at you. Say, oh yeah, look at that one right there. Okay? So when you look at this, I ask this question, do you recognize this? Looks like spherical. So remember when we were doing spherical coordinates, we did a substitution. You remember what the substitution was? It was like x is equal to rho cosine theta sine phi. Y was equal to rho sine theta sine phi. And then z was equal to rho cosine phi. Do y'all remember that? Spherical coordinates. This is what we did. And we had some restrictions. We had theta was between 0 and 2 pi. And phi was between what? Remember, phi was that angle. I stood in the corner. I said phi is this way. 0 to pi, right? Not 2 pi.
You just do the first half and then do the equation.
No, pi goes all the way down.
Yeah.
Yeah.
What am I asking?
Yes, you only go there, but you rotate all the way around, so it gives you the whole sphere. Right? Okay, now, look at this vector function. And do you see that that is this? Do y'all see that or no? Just making sure I wrote everything down right here. Okay. So, what's rho in this problem? 1. And instead of, which one of these, this one right here would be equivalent to what theta would be, right? And this one right here would be equivalent to our phi. So
The other way around.
basically this should draw,
No.
these are switched, okay? These are flipped from this formula. But it's multiplication, so it doesn't matter. That should draw the unit sphere, right? Surface, that's what it should draw, okay? And I have an animation that shows you this. And it's too big. There we go. Okay, so here what I want you to imagine is that you have a domain, okay, D. And our domain here is the U and the V, right? U is between something, V is between something. So if I let U go between 0 to pi and I let V go between 0 and 2 pi, then if I pick some point, some ordered pair here, some UV point, then plug that in to that vector function, it should give me a three-dimensional point, shouldn't it? And here's where that point would be. If I fix, let's fix my U to be right here, pi over 4. And let's let my V vary. So if I let my V vary and I fix my U, it's going to, see that point moving along? That's called a grid curve. All right? It's going to draw me that circle. And then if I change U a little bit, let's drop U, let's make it go down a little bit more there. And then I let V go, I'm going to draw that one, right? And basically you get all the latitude and longitude lines, and, right? I mean, that's basically what's happening here. All right, these are called grid curves. And you could do that for any surface, really. You got to hold one constant, and then you start drawing, and then you move the other. You change that constant a little bit, draw it again, and when you put them all together, you get your surface. Doesn't matter which one you hold. Yep. See, because if I change my U, it goes. You know, that's your up and down on the surface, and then your V is your circles. Grid curves don't have to be closed. No. Mm-mm. The only reason that is because it has sine and cosine in it. All right, now let's see if we can remember the meaning of the derivative of a vector function back when we were doing space curves. These were three-dimensional curves, not surfaces. We're talking about surfaces now, right? But when we were talking about curves, space curves, when we took the derivative, so we had some curve, and we could move along that curve, and when we took the derivative, it would give us a vector that was tangent to our curve at that point, right? And it was a vector. So r prime of t gave us some sort of three-dimensional vector that has both length and direction, right? Well, in two-dimensional, with surfaces, vector functions of two variables, we can take a derivative, but it would have to be partial derivatives because we have two variables now. And the question is, what would they mean? So if you take the derivative of this vector function, r of u v, with respect to u, that means you hold v constant, right? Then basically what you're doing is you're moving along one of those grid curves, right? And looking at that tangent vector off just that grid curve. So here's that same idea that we just had. Okay, so there's your sphere again. Notice you have the dotted green would be one of the grid curves if we held, I think this was u, right? If we held u constant, right, and let v change, then we'd be moving along the red, right? But if we held v constant and let u change, we'd be moving along the green. Understand? So if we're moving along the red, at any given point I have a tangent vector, don't I? And then moving along the green, at any point I have a tangent vector. So you've got these two vectors, don't you? And guess what? If you cross them, you get a normal vector. And you actually have a plane there, don't you?
Yes.
You have a tangent plane. A plane that's tangent to the surface. Right? And that leads us to this. Given any surface with a vector function r of u v, where u is in the domain D, we can find the equation of the tangent plane at any point on the surface. We can find the equation of that plane. Now that plane continues forever, but the idea there you can see comes from those two partial derivative vectors. And we're going to do that now. So let's find the equation of the plane that's tangent to the unit sphere at this point. All right. So, first of all, what is the equation of the tangent? What is the vector function that gives us the unit sphere? So r of u v equals, so you can write this several ways, but I'll do it the way I presented it earlier, right? So we're using the same thing, sine u cosine v, and then sine u sine v, and then cosine u. And let's put our restrictions. U is acting like the phi. It's between 0 and pi. And v is acting like the theta was. So 0 to 2 pi. OK, that should draw me the unit sphere. This right here draws unit sphere. OK. I need to find the equation of the tangent plane, right? Now, the equation of any plane, the equation of a plane is a x minus x naught plus b y minus y naught plus c z minus z naught equals 0. That's the standard equation of a plane, right? But that a, b, and c are very special, aren't they? The a, b, c, if we write it as a vector, we called that the normal vector, didn't we, to the plane? Now, they're asking us to find the equation of the plane that's tangent to the unit sphere at this point. So I already have x naught, y naught, z naught, don't I? I just need to find the normal vector. But that normal vector is going to come from where? We're going to do the partials and cross them. So this is actually, we're going to actually get that by taking the partial of r with respect to u and crossing it with the partial of r with respect to v. Those are those two vectors we just saw crossed together, gives us our normal. Now that normal, remember normal vectors, when you have this vector ABC, if I scaled this, if I doubled it, it would still be a normal vector. As long as I'm parallel, then it works. And the cross product will be parallel. So let's take the partial of r with respect to u. We haven't done that yet. What is the partial of r with respect to u? Well, it's a vector, isn't it? And what would the derivative of this be with respect to u? So how do I do that? I just derive each component separately, right? Derivative of this with respect to u? Cosine u, cosine v. Cosine v is like a constant, right? Derivative of this with respect to u? Cosine u sine v. And then finally, derivative of that with respect to u? Negative sine u. Okay. Now, I have the partial with respect to v next. So I'm going to put that right below it. Now, I like to put it below it because in the next step, I'm going to do the cross. And it's nice to have them stacked above each other like this. So what is the partial of this with respect to v? So I'm going to have a negative. So negative sine u sine v. And then here, sine u cosine v. And finally, 0. And now let's cross the two. When I do a cross product, I get a vector, don't I? All right, let's take our time. To do the I component, which is this component, we cover this one up and we do a little determinant on those, right? So when I do my determinant, here to here I get 0. And then here to here I'm going to get a negative, but then I'm going to subtract it. Right? I'm going to get negative from this, but then I subtract, so it'll become plus. And it's just what? Sine squared u? Cosine v. Okay. Now we take the middle one, cover it up, and we do a determinant here, and we change the sign. So when I do this times this, it's 0. Minus this times this, but that's a positive, so it's going to be minus, but then you change it. It's plus, right? It's going to be plus. Look, when I do the cross products, when I get to the middle one, I just do it backwards. That's the way I do it, and I don't worry about changing the sign. So I do this times this minus this times this, instead of this times this minus this times this. It's the same thing. It takes it all in one swoop. So if I do this times this, I get positive sine squared u sine v. And then minus that, but it's 0. With me? Okay, last one. Cover up this one. Sine u cosine squared v. Sine u cosine u, what did we say, cosine squared v? Crap, I'm going to run out of room. Minus, but then it's a minus, so plus, right? Plus cosine u sine u. I'm going to write it sine u cosine u. And then sine squared v. And do y'all see that that last component can clean up a little bit? You can factor out sine u cosine u, pull that out, and then you have cosine squared v plus sine squared v, which is 1. So this is just going to be sine u cosine u. There's our cross product. Okay, wait a minute. What the heck are we doing? All right, we know back here with this equation, we know x naught's what? Root 2 over 2. We know this is root 2 over 2. We know y naught is 0. And we know z naught is root 2 over 2. Our goal was to try and find a, b, and c, which